So it's my great pleasure to introduce our next speaker, Carolyn Matl. So Carolyn is a research scientist at Toyota Research Institute, where she worked on robotic manipulation with the mobile manipulation team. She received her doctoral degree from the University of California, Berkeley, where she was advised by Rosanna Baichi and was supported by the NSF Graduate Research Fellowship. Her research focused on developing and leveraging interactive perception for the robotic manipulation of complex material, such as liquid, grains, and dough. Outside of research, she enjoyed cooking for her friends and family. And I can personally attest that it's very good.
Yeah.
All right, go ahead.
Thanks, Daniel. So yes, as you said, I'm Carolyn Matl. Thank you so much for having me here today. This is an amazing crowd, like feeling a little stage frighty. First time talking to a live audience in a while. So I am a research scientist with the mobile manipulation team at Toyota Research Institute. And prior to joining TRI, I was a PhD student under the advisorship of the wonderful Rosanna Baichi, who's here right now. And there for my dissertation, I focused on, as Daniel said, the manipulation of complex materials like liquids, grains, and doughs. So today I'll be presenting the latter half of my thesis, how we designed a soft tactile hand and used it to manipulate deformable Elasto-Plastic materials like dough. So this presentation draws from two works that were published last year in 2021. The first at ICRA, which we were honored with the Best Manipulation Paper Award, and its follow-up paper, which was published at IROS. Both were remote presentations again, so it's really lovely to have this opportunity to revisit this work with this audience in person. Okay, so before we begin, let's first talk about what even is a deformable Elasto-Plastic object. So in our work, and in fact, many works that simulate these types of objects, we categorize doughs as 3D Elasto-Plastic objects, or in other words, objects made of materials that exhibit both elastic and plastic properties. So a simple illustration of this characteristic should be very familiar to those of you who cook or bake. When you press into dough, some of the dough springs back, but there's also some permanent deformation that can result from this forceful interaction. So modeling this type of material sounds a bit complex. And even so, we're already technically simplifying it by considering it as elasto-plastic, which is rate independent of the applied loading force, instead of viscoelastic, which is rate dependent. Luckily, in the context in which we have our robot interact with our dough, time is less of a crucial variable, so we can settle for this simpler material representation. Okay, so given the characteristics of soft deformable material like dough, which has these regions of elasticity and plasticity, we wanted to come up with a way to interact with this type of material delicately. So to enable both the perception of the geometry and stiffness of the material without creating any unwanted permanent deformation. So this would be perceiving within this elastic region, but we additionally wanted to enable intentional deformations of the material through interactions with sufficient load force. So this would be acting within the plastic region. And ideally, we'd like to also optimize how we interact with and manipulate these materials. And we want to explore these ideas within the context of shape zeroing. Okay, so this talk will address these challenges, challenge criteria in two parts. So in the first, we'll discuss how we designed a variable stiffness soft tactile hand that was used for both sensing and imposing load forces on deformable objects. And in the second half, we'll examine how we can use this new technology to efficiently shape servo pieces of dough with model-based reinforcement learning. Okay, so the first set of criteria ultimately led us to design this really simple hand made of soft compliant material, which we called stretch. And so the robot could vary the stiffness via a simple actuation mechanism by stretching the membrane. So the soft tactile end effector that we designed can be categorized as a very simple soft optical tactile sensor. So meaning that the tactile interface is made of soft compliant material, and when the membrane surface makes contact with the environment or an object, its deformations are imaged by an optical sensor like a depth sensor. So I imagine that many of you here probably have worked with these types of sensors in your own work or may recognize some of these examples, so I'll just briefly go over them. So on the left, the gel site sensor and all its iterations like the gel slim from MIT or the digit finger from Meta, these are all quite popular due to their high resolution contact images. In comparison, the four pictured on the right have arguably higher compliance, which opens up a lot of applications where soft contact makes interactions safer or more robust. So for example, the TAC tip from the University of Bristol explored performing tumor detection, while the soft bubble from Toyota Research was used to handle delicate objects like a wine glass. Isabella, who we just heard from, used her own soft optical tactile sensor to support human arms and even help wipe or bathe humans. So now in the middle is the first soft optical tactile sensor that I designed at Berkeley, along with my colleague Ben McEnroe. And this sensor was heavily inspired by the TAC tip from Bristol, except that instead of filling the fingertip with gel, we created this pressurized capsule full of air. So let me briefly explain why we did that. So because we were using pneumatics to maintain the shape of the fingertip, we could also leverage this actuation mechanism to stiffen the silicon membrane by increasing the pressure inside the capsule. So not only could this device act as a tactile sensor, but it could also act as an actuator and automatically adjust its stiffness to compensate for slipping. So for instance, to hold up this container that has dynamically changing mass. So in this prior work, we really were studying this sensing and actuation duality and found that variable stiffness tactile sensing had a lot of potential in expanding robotic manipulation capabilities, including the manipulation of deformable materials like dough, since we could leverage the fingertip in its soft regime to sense by interacting with the object within the elastic region. And we could also use the fingertip in its stiff regime to apply sufficient load forces to cause plastic deformations that we intended. But note that at the same time, there were a lot of challenges while working with this prior design. So for one, it was pneumatically actuated, so this made it difficult to controllably vary the stiffness of the membrane. And overall, this was quite difficult and tricky to manufacture. So fast forward to year 2020, year of the lockdown, when we wanted to revisit this problem, but at the same time, access to major design and fabrication centers was basically revoked. So all of these challenges motivated the design of Stretch, or soft to resistive elastic tactile hand, which we were able to make with supplies I basically had already in my living room. So as you can see, it's composed of a flat elastic membrane that can be cast very easily by pouring EcoFlex silicone into a rectangular mold. And we attach this membrane to a parallel jaw gripper using Velcro. And so instead of varying stiffness via pneumatic actuation, here, as the gripper increases its gripper width, the membrane's internal strain increases, and this subsequently increases the stiffness of the membrane. And so you can imagine that this actuation mechanism makes variable stiffness much easier to control. So we use a depth sensor to image the deformations of the membrane when it's in contact with an object. And with the assumption that the object is convex, the robot can extract out the portion of the membrane that's in direct contact with the object. So you can see how it's really a bare bones, like very simple flat version of the optical tactile sensors that we saw earlier. Because Stretch was so compliant, we were able to use it at its low stiffness regime to reconstruct the geometry of very deformable objects like paper boxes or 2D wire shapes like this circle through touch. And because Stretch can vary its mechanical response, we can estimate the stiffness of deformable objects as well via active palpation. So the graph on the right shows multiple indentation depth to load force curves that correspond to different stretch states of the membrane, where the higher curves correspond to the membrane being stretched more. And ultimately, we want to find the force at which the object finally deforms. Since if we imagine this object as having a single degree of freedom, we can divide this force by the amount of deflection to estimate a proxy for its stiffness in newtons over millimeters. And so we can use this force depth profile to actually save time and efficiently modulate the stiffness of the membrane so that the load force increases monotonically with each new contact condition. So instead of starting from the lowest indentation depth every time the membrane is stretched, we can jump up this ladder, as you saw here, to the next indentation depth that would result in the closest increased load force. And this allowed the robot to efficiently approximate a stiffness value for the object. So the robot measured the stiffness of 4 balloons filled with different materials, as you see here. And even though these are technically, again, proxy values for stiffness, since we're using this simple 1 degree of freedom model, you can see that the values increase with each object as we would expect. And the estimated values are sufficient for differentiating between materials within this range. So just keep this in mind because we'll be reusing this proxy for stiffness in our dough rolling work, where this estimate actually enables more efficient rolling. So for this first iteration of the sensor, we chose to use the robot to roll blocks of Play-Doh into balls of dough as a way of demonstrating the range of capabilities this simple sensor could offer. So first, stretch was used to measure the membrane stiffness needed to deform this block of dough. And once the robot measured how much the membrane needed to be stretched, it was commanded to roll the block of dough in circles, tracking the position of the dough in parallel to ensure that the robot was able to maintain contact with the dough while still being stiff enough to exert force on the block of dough. So this goes on for quite a bit, but once the robot thinks that the ball is round enough, it'll stop rolling the dough. And so stretch, and then in a second, you'll see that stretch is used at its lowest stiffness to measure the geometry of the ball. So here it's estimating its diameter. And then finally, stretch is used at its highest stiffness regime to press the dough ball into this sort of scone shape. Okay, so for the most part, you can see here that the robot was able to shape these blocks of dough into circular cookies. So we wanted to use this demonstration as a way to illustrate how we could use variable stiffness soft tactile hands to safely sense the geometry and stiffness of very deformable objects, while also having the capability of imposing larger load forces to make intentional deformations, therefore enabling new robotic manipulation capabilities such as dough rolling, shaping, and flattening. So the next step is, how can we use this technology to more efficiently shape servo this type of material? Dough rolling the dough rolling that I showed earlier was based on a heuristic algorithm that sometimes took up to 20 minutes to execute. So, but we know humans can do this so quickly. So we must be able to do this more intelligently. Okay, so that's pretty much the goal for the second half of the talk. We'll talk about how we used model-based reinforcement learning to accelerate the task of rolling out dough into a breadstick of a specific length. So for this iteration of stretch, we made the entire end effector attachment out of elastic bands. And you can see here it's a slimmer version than the prior version. The depth camera was also fixed at an overhead position instead of being rigidly attached to the robot arm. And these design changes were mainly to compensate for kinematic limits required of the dough rolling task. Okay, so however, notice that the task of dough rolling requires dynamic interactions of a deformable end effector with a deformable object. So this is highly complex and high dimensional dynamics that are difficult to model, and as we heard earlier, even to simulate. So instead of explicitly representing the dough to hand interactions, we used model-based reinforcement learning to learn a transition function for these interactions. So meaning we learn from data the relationship of, given an action applied to the dough and its current state, what will the dough state be after that action is applied? And so that model is represented by F here. Now within this framework, we use model predictive control to select the best action to take at this time step given the current state of the dough. So this is done by optimizing the cumulative expected reward over the over a certain number of time steps into the future. So we're looking ahead, where at each time step reward is calculated simply as, well, in this case, how close are we to the desired goal, dough formation. And what the reinforcement learning framework adds to model predictive control here is that it allows us to iteratively update or improve the transition model F to better reflect the dynamics of the dough and hand interactions. So this means that if we start off with the wrong model or a poorly initialized model, then the algorithm still has time to self-correct. So I know I did just mention that these interactions are extremely complex. So this brings up the question, and a question that we think in this community a lot about is like, how do we deal with such high dimensional data? In our case, because our goal was fairly simple, we were able to simplify the problem with some engineering to make it a lot more tractable. So to simplify the state space of the dough, we took the dough formations bounding box and used those dimensions to track the dough's shape progression over time. As for what actions to apply to the dough, well, the two things we decided to vary were the stiffness of the hand's elastic membrane, which we could vary by stretching or closing the gripper, as well as the depth at which the robot pressed the dough. These two parameters were chosen because they directly affect the load force imposed by the elastic hand. And the rest of the robotic action was fixed in that each roll consisted of a back and forth motion at the highest point of the dough formation. So given all these simplifications and action constraints, we were actually able to train a dynamics model of these interactions with only about 1 hour of robot time, where the robot randomly interacted with the ball of dough under these action constraints. Okay. So as we can see here, comparing the reinforcement learning methods with a random and heuristic policy, all of which were under the same state and action simplifications and constraints, the robot was able to roll the dough out into this 6-inch log with significantly fewer rolls. And also the robot was able to efficiently roll the dough into different length breadsticks up to basically a foot. However, what happens if the dough that is being manipulated now is not the same dough as the one that was used for training? Maybe it could be a drier dough, which could cause it to be less malleable or stiffer. It could also be more well rested. So this means it's much easier to plastically deform. And this is a really real problem because if any of you are familiar with working with dough, the feeling of the dough can change quite quickly. But because this is a model-based reinforcement learning framework, it allows the robot to iteratively improve the dynamics model, given new observations as the robot in real time interacts with the dough. So let me replay that. Oops. Okay. So here we were able to show that it's able to self-correct and efficiently roll out a stiffer dough much faster than compared to when using a fixed model using just MPC. But you might ask, well, in our prior work, we showed how we could use stretch to approximate a proxy for the stiffness of these objects. Wouldn't it be great to use these estimates to calibrate the model more quickly so that we can more efficiently roll out the dough? And yes, you would be absolutely correct in that it does help. So here we're showing our robot measuring the stiffness of these 3 different doughs that are hydrated at different hydration levels. And we were able to demonstrate through our experiments that these stiffness measurements do indeed help the robot regress to a better dynamics model for the dough and interactions. And this leads to significantly more efficient rollouts. So if the robot sensed that the dough was soft, it would use a different rolling technique than if it sensed that the dough was hard. And the actions chosen by the robot actually made a lot of intuitive sense. So for instance, for a hard dough, the robot chose to apply actions that corresponded to higher force output versus when it sensed that it was a softer dough, the robot chose to first apply low force to the ball until it formed into a short log, and then it started increasing the membrane stiffness to finish rolling the ball out into a longer log. So as a brief recap, through these 2 works, we explored how we could use a very simple variable stiffness soft tactile sensor to sense the contact geometry of very soft deformable objects, as well as to measure a proxy for stiffness for deformable objects. And finally, to use that information to efficiently shape servo dough. I'd like to say, though, that there are several avenues of future work to explore here, since we really viewed this work as a stepping stone into new directions for soft robotic manipulation and sensors. So, future work includes, for one, while our simple state and action space of the dough allowed us to simplify the dimensions of our problem, a higher dimensional space would certainly allow us to explore more interesting shape servoing problems, as well as to allow us to create a tighter sensory action loop. Furthermore, there's been a lot of great recent work on modeling deformable contact and deformable objects, some of which was presented today. So I would love to see how those models could be incorporated to in a robotic system to deal with materials like dough. Finally, because this work was done during COVID times, Play-Doh made the experiments a lot more manageable to do in a household setting, but the dream would be to shape real dough, which is way more elastic, way more malleable, sticky, and tricky to deal with. But at least at the end, you could actually eat what you make. So I just wanted to take this opportunity to thank my collaborators, Rujna, Isabella, and Josephine, as well as the ICRA workshop organizers for inviting me. This was a really great opportunity. If you have any questions, don't hesitate to reach out to me at my new email. I also just wanted to give a little plug that at TRI, we work on related problems for deformable object manipulation, and we are working on things like dough rolling or food prep. So we are hiring at TRI, so don't hesitate to reach out if you're interested in a role there. Great. Yeah. Take questions.
Yeah, thank you very much for the great talk. I think we can take maybe 2 questions from the audience, and then we'll move on to the panel discussion, which concludes the workshop. But if anyone has any question for Carolyn, please, please like line up or ask online. I think we have one. Yeah.
Great talk.
Thanks.
I'm curious about the stiffness of the object.
Yeah.
So you showed some numbers for like the soft dough or hard dough. Is that relative, or is that some number you can actually like trust as like the softness or hardness of the object?
Yeah, so again, I mentioned it's a proxy for stiffness because we use a one-dimensional model, but it is a actual number that you can measure, if that's what you were asking, because it's based on basically the state of the soft hand, so how far it's stretched and how far it's pressed into the dough. And based on our model of the sensor hand, we can estimate the load force that it's imposing onto that object. And so taking that load force and the amount of deformation you actually sense at that contact condition, you can just basically divide the force by the deformation to get this one-dimensional estimate of stiffness. Yeah.
And the accuracy seems to be like hundreds of newtons per.
Yeah, it was within 1% of the operating region of basically the load force that we could measure. So it was fairly repeatable. So that gave us confidence that we could, even though this might not be the most accurate representation of stiffness, it was enough, it was sufficient information there to help us accomplish like more efficient dough rolling, for instance. Thanks.
All right, let me just check online. So we don't seem to have any more questions. So thank you again.
Thanks.